Hello, 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 we, she, and hello. All right, right on. All right. Oh, wait, there's more people. Okay, okay. Oh, wow, you all beat me. Wow, amazing. Okay, sorry. Hello, hello. Oh, look at that. Okay. Let me, no, more people. No, let me not start. More people coming. Hang on. Hang on. Um, oh, not more people. I don't know if the waiting room is like, maybe the waiting room is the next idea, but good afternoon, Andrew. Hello, Charlie. Good afternoon, Vivian. Hello, and good afternoon, we, she. Good afternoon, Catherine with a I. Good afternoon, Warda with a A. Good afternoon, Jay Lynn with a J Lynn. Good afternoon, Alyssa with a Brunatelli. Good afternoon, Catherine with a Y. Hello, Michaela with a because. Oh, hold on, more people coming. Sorry. Okay. Good afternoon, Lakshmi with the NPR news broadcast. Good afternoon, Stephanie. Good afternoon, Gabriella with a Yi. Hi, Celine. See, I can never, even if yeah, anyway, you get it. All right. Good afternoon, Jayla. Good afternoon, Rachel. Okay, and now I'm going to go back, circle around to the whole. Now I'm doing video. Good afternoon, we, she with the video. Good afternoon, Gabriella with the video. Good afternoon, Jayla with the video, which I appreciate totally. And notice, good afternoon, Catherine and Stephanie with the avatars, and Vivian with, oh, sorry, and Michaela with the avatar. I can't even pronounce that word, with the images, which I totally appreciate. And Vivian's, Vivian drew hers, I believe, which I would have never known, except it was in an assignment, and I hadn't noticed it before. But anyway, all right, I'm impressed. I'm impressed with everybody, but I'm impressed also with the black boxes. Good afternoon, Lakshmi, Jaylene, Catherine, Alyssa, Andrew, Charlie, Warda, and Celine, and Syed, who's named after decades. I still, he claims I pronounce it correctly because he's very polite, but I think he's being very polite. But okay, but there's nothing wrong with politeness. What do they say? Politeness. It is correct. All right. Well, thank you. All right. Cool. Cool. I don't know why I feel so insecure about that, but that's because I'm an insecure guy. What do they say? Politeness costs nothing. All right. But thank you, Syed. I appreciate it. Okay. We're gonna start. We're gonna start. We're gonna start. We actually have things to do. Wait, that's funny, Gabrielle, especially because who's your lab prof? I thought you don't have a lab prof. Well, you do as of tomorrow, which I was going to talk, but okay, fair enough. Oh, and someone's coming, more coming. Okay, okay. So we're going to start in a second. For anybody keeping score in that chess game, I totally lost. And then that obnoxious, amazing guy whose name shall remain nameless, he totally beats me in that chess game. Then he has the audacity to show me afterwards. He's like, oh my God, you almost had me. Did you see how you almost had me like 17 moves ago? Did you see how you almost won? And then like sends me a whole like animated thing of like a replay of what if I had only done this one, how I had him in this amazing position. And if I had only actually had a brain, then I would have not even won, but like drawn. And he shows me this. Now you tell me, am I supposed to feel smarter or stupider after? Is that, I mean, only a winner can do that to a loser. And there's no way the loser feels less like a loser after that. But anyway, okay. No problem, no problem. You've missed nothing. Cool, okay, I appreciate it. Okay, we're back to that. Yes, with an artificial intelligence, I can beat him. And sometimes I wonder if the intelligence I do have is in fact not artificial. But okay, but yes, I will cheat someday. Yes, it's the only way to beat him. Okay, we're gonna start. We're gonna yeah, that's actually all right. Fair point. He could be, in principle, he could be cheating, except I know he doesn't have to, and he knows he doesn't have to, so why would he? But yeah, I mean, also, he's even more moral than I am. He would, but yes, you're right. I don't actually know that for a fact. Okay. So we're gonna start. we're starting to make tracks with the material here. So the real bad news for you guys is soon you're actually going to have more homework. It's not like I've totally forgotten, not tonight because I can't handle it, but I have to give you back the homework you still have done and haven't gotten back. But soon we're going to have to start doing more work. But we're going to get back to the material, to the end of question 9. One thing announcement, maybe you definitely, I'm so thrilled to say this, you are definitely having lab tomorrow. You are definitely meeting Professor Johnson tomorrow. He's definitely totally psyched. We have all the letters of clearance, blah, 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 blah. I'm excited. And I'll warn you all too, this is a real thing. So you'll have lab tomorrow. Please meet in the lab room. Please meet Professor Johnson. Da, 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 da. It is and I'm going to tell you also right now, it's going to be like very much like the 2 labs I did with you guys, in that there's like a specific purpose to the lab, a specific point, like a takeaway that you get from the graphs. It's kind of like you want to see the shapes of these 2 relationships that you're going to try to get, and you'll see them in the graphs. And if you can get to the 2 graphs, then you're done. Thank you very much. Everybody loves everybody. Like, for one more time, we're not expecting or attempting to do a lab report or anything like that. We're still trying to get this whole system comfortable at a comfortable pace. So that's the good news, is like, just like last 2 times, it's about doing something, doing it, getting the result there, and then leaving. I'm also going to warn you though, and he knows this, the lab for tomorrow, I mean, is cool when it works correctly and when people do it correctly. It actually will bring you to some new interesting material, honestly. On the other hand, it is there's a lot of technical aspects to it. I shouldn't say technical. I mean, there's technology aspects to it. Like you are going to be getting data. You're going to be, I don't want to ruin the whole thing, but you're going to be taking a movie of stuff with your phones, like honestly, with your own like iPhones or Samsung phones or whatever. You're going to be importing those movies into the laboratory laptops. You're going to be taking data with Logger Pro. Maybe someone should remind me. Can anybody remind me in the chat? I can't remember now. Have you guys used Logger Pro software? I know I've done stuff with you. I can't remember. Tell me in the chat whether you were in this class. I mean, yes. Okay. Thank you. I thought so. Okay. So that's good. So that means that's already like one potential problem slightly mitigated. So you're going to be making movies with your phone, not fun movie. I mean, not exciting, but you're going to be taking data visually with your phones. You're going to be exporting or importing that data into the laptop computers in the lab. You're going to be using Logger Pro to extract data from those movies. I mean, and this is real. Like, I'm not trying to get all, but and then you're going to be turning that data into a pair of graphs. Well, first tables of values and then pair of graphs. That's the program. Things can go wrong. I mean, since you've already used Logger Pro, that's the good news. So hopefully nothing will as such go wrong with Logger Pro. And since you've already had success logging into the laptops, hopefully this will all go smooth, but just be patient and know, just like the last 2 times, that really there's no need to rush. Really, the goal of the lab is not it's not meant to be overly ambitious. It's meant to build in time to play, experiment, like have a little fun, whatever that means. Let things go wrong and then error correct, like try and error on your own as your groups, the same groups that you had last time. Like, just be a little patient with yourselves and with the data collecting process, because it does have some subtleties. And they will take you maybe more time than any deep thought that you might think we're expecting. So I'm just basically saying, everybody be patient with one another and know that you don't have to rush, and that when glitches arise, that's part of experimentation and built into the time schedule. I'm saying all this, even including the glitch that might arise of, do we know for a fact that the key that is necessary to unlock the cabinet to get you the laptops, do we know for an absolute fact that that key will be accessible to the people that need it to get you those laptops tomorrow? No, we don't. I'm going to try to correct for that problem in the morning. Like this is something, but I'm just saying little things could go wrong. Just roll with them and know that we're rolling with them too. But it is a very cool lab. It is, if you can get to the conclusion. It's a very cool, okay. Okay, yes, be ready for, okay, you did, right, you did the photo kits, right. Okay, well, thank you for all answering. Wow, that also, remember the participation thing, you're all, what happened last week? Wait, what happened last week? Oh yeah, you totally can't. Okay, wait, what happened last week? Wait, sorry. Okay, I'm looking at the direct chats and the public chats. Hold on. First of all, I appreciate everybody that put an answer about the photo gates and everything in the. So last, and I do want to move to the material today will help. By the way, I'm very much have your lab on my mind for tomorrow. So I will tell you that the material we're doing today, even though it is to wrap up question 9 of homework 1, it's very related. The lab tomorrow will be a step up and forward from this material, but the more you actually understand the material today, the more it will help in the lab. Just to answer the question, as far as last week, someone's asking, I'm not going to say the names, it's direct chat, but someone's asking what happened last week. If you're asking what did we do in the lab, the answer is nothing. We didn't have lab last week. No one missed anything. If you're asking why, I'll tell you right now. I mean, there was actually a number of reasons. The main reason your lab, okay, it turned out we canceled all the physics 204 labs for last week. Okay, so nobody's behind or anything like that. Different things actually happened in the different labs. The reason your lab was canceled is very simply that even though Professor Johnson was totally ready to go, and I was ready for him to go, we were all like ready to go just on a human resources, like just on a pure university paperwork level, they had not sent him his paperwork clearance to teach yet. Like that just took longer than it should have. I mean, he got hired in the middle of the semester because we had a thing and blah, blah, blah. So within our department and academically, we were all ready, but just employment wise or paperwork wise, he wasn't cleared legally to walk into that particular room and teach in this particular program yet. Like the university had to clear him. So it took, and the clearance came like 2 days later, but it wasn't in time for that day. So I was stupid annoying. And it's one of those rules we have to follow. It's ultimately like part of lab safety and all that. Like we can't have a person in the lab who's not cleared. So anyway, it's not interesting, but that's all that happened. So it was nobody's fault. It was like an administrative bureaucratic thing. And it was unfortunate, but now it's all clear. So he's good to go. Okay, no, thank you. Sorry. And and then other related things happened in the other labs, but okay. So we're going to get back to so I appreciate all your patience and and yes, to the other direct chat person. Yeah. So yes, I would certainly, how can I, hold on. I'll just hold on. Sorry. I'll be with you all in 1 second. And I know someone's in the waiting room. I'll let them go. I'll let them in 1 second. Sorry. Thank you. Okay. So what we're going to do now is we're going to get back to the lecture material that we were doing. We're actually at a big frothy point now in the lecture. Like we're actually onto a big sort of conclusion, or technically we arrived at it last Wednesday. I want to back up like a step or two and reinforce that conclusion to which we arrived. But again, please understand this all points toward, like we're wrapping up question 9. We'll get a numerical answer to make ourselves happy. But really, this is like this is a big takeaway of material for the future of the semester and for lab. So, okay, so bear with me. And I'll look in the chat in a moment. Sorry. Um, okay. Look in the chat. Okay. All right. Now I'm just review again. Technically, at the end of last Wednesday, whether we were all together or not, technically, we in my mind we finished question 9. Although we did not get a number, we didn't get a numerical answer. So we'll do that in a moment. But technically we were working on question 9. But really, the reason it took us like 2 days, and the reason that the whole sheet took us like 4 weeks, is what we've really been working on. I can sort of now say to you, and what we've been working on in the labs is, given a show, an SHO, a simple harmonic oscillator. Okay, this is what we're really dealing with right now, is given a simple harmonic oscillator, what is the equation of motion? What is the relationship between position and time? Like, that is really our larger physics question that's been on the table. And again, it's an important question. So, and what is a simple harmonic oscillator? Like as you might have even seen in lab 2, a simple harmonic oscillator is anything that acts like a mass on a spring, but lots and lots of things in the natural and the technological worlds act like masses on springs. To act like a mass on a spring is really to be a system that is subjected to something like Hooke's law. And I'm going to be more specific about that in a minute. But really what we're dealing with here is any kind of system for which the dependent variable, the measurable dependent variable, whether it's linear position, as it is in this case, or angular position, as it might be for a pendulum, or temperature, as it might be for the next homework problem we do, or electrostatic field. If you're measuring some aspect of some system, and if that thing that you're measuring is subjected to a linear restoring force, if the thing that you're measuring is always being pulled back to some equilibrium value in a manner that's directly proportional to it itself, then the system is a harmonic oscillator. And then we are trying to find, and then what we want is, well, how does the value of the dependent variable depend on time? Okay, like that's like the general thing for us. And in general, a simple harmonic oscillator is something that is a system, is an oscillating system. But to call it harmonic is to say that the oscillating system is regularized, is controlled and predicted by a linear restoring force. So I'm going to be more specific now in a minute. And again, I know we want to get a number here, but we also want to remember that the number is not really the big takeaway. So what we're really getting at here is i.e. Well, I'm sorry. So technically what I'm doing right now is technically I'm reviewing, but fast from last Wednesday, just to show you the whole argument that we're making here. Right. So okay, so just again, just like what we're really saying, okay, Hooke's law is F equals negative kx, right? But force equals mass times acceleration, right? And net force equals, and in the kind of system we're talking about, the Hooke's law force is the only force acting. So we do a little rearrangement, a little algebraic rearrangement, a little generalization, a little throwing in the definition, and what we find is that really the mathematically general way to say Hooke's law really in general is to write this second order differential equation, right? Like that's what we established like last Monday or something. That when I say from here on in Hooke's law, if I really mean it in a broad sense or in a mathematical sense, if I want to apply what the concept of Hooke's law to masses on springs or to pendulums on strings or to temperature systems or to electrical fields or blah, blah, if I want to apply it to any imagined dependent variable, what I'm really saying about Hooke's law is really saying that we have a situation where the second time derivative, the rate of change with respect to time of whatever variable we're talking about, whatever dependent variable we're talking about, is directly proportional to that variable that we're talking about, right? That this differential equation says that. It says, given some x, the second time derivative of x is directly proportional to x itself. When I say directly proportional, I'm saying that because, sorry, let me make it different. I'm saying, so I'm saying from here on in, if I think simple harmonic oscillation, I think this differential equation says this, the time derivative of the variable, of the measurement that we care about, is directly proportional to the variable itself. Now, what does directly proportional mean? It means equal to some constant times the variable itself, and then times a negative sign. The negative means that the rate of change is always opposite in direction to the variable itself, i.e. it's always restoring it back to some equilibrium orientation. Like if the variable x is positive, then that negative sign will mean we're pulling it toward the negatives. If the variable happens to be negative at some moment, then the negative sign is negative of a negative. It's pulling it toward the positive, right? The negative sign must be there. I mean, let me be clear about that. There, you could write a differential equation like this one that doesn't have the negative sign. That would still be a valid differential equation. There would still be a solution to it. It'd be interesting math, but it wouldn't describe, it would be a different differential equation. It would not describe harmonic oscillation. This here is the essence of harmonic oscillation. I'm even going to go one step further. Okay. Now, and well, actually, Let me think for a second. Do I want to do this or do I want to do that? I want. Okay, no. So what we found, so this was a differential equation. It's not an answer. It poses a question. We found I will look at the chat in a second, but okay. So we are still technically reviewing here, but we found and I will look in the chat in a second, but we found a solution to the above, and we did it through some sort of guess and check and verify and differentiate thing, which I will. Wait, okay, I'm totally gonna look in the chat in a second. I'm a little worried. I have a bad feeling about what kind of things are in the chat at the moment. I will look, but please note again with me, like what we have here is an equation, but it's a differential equation in that it is an equation, but it doesn't, and it contains the information we want, but it does not present explicitly the information we want. What we wanted was X as a function of T, and I will look at the chat, but what we found, right? We found a solution. We found at least one. It might not be the only one, but we found AX such that when it's differentiated twice with respect to time, it gives back itself times a constant times a negative sign. Like that's what we're looking for. And this is, again, like reverse engineering. We're looking for a function that does this thing here, right? And we found an example of a function. We sort of guessed it. We sort of constructed it. We sort of weren't sure. We sort of used lab knowledge to construct it. But then we verified it. We found a function, and the very last thing we did last Wednesday was we differentiated it twice, and we found, oh yes, when we differentiate twice, we do get it back itself times a constant times a negative. So it works, we said. Now that happened right at the end of class last time. That's why I'm reviewing this, and I will look at the chat in a second. But what I'm saying is what we found last time, something like this. Right now, again, and I will pause in a second, look in the chat, but notice, like, or we found, or we conjectured, I get, well, okay, I'll say we conjectured. We first conjectured. And the reason I'm calling it a conjecture at first, even though it's right, like, and I'm going to show you again very quickly that it's right, but the reason I'm even going to call it a conjecture again is, like, when we made it up, it had these letters in it, X naught and omega, like, and they weren't anywhere in that differential equation. Like, I just made up this omega thing. So of course I had to, like, that just made that up. Like, how do I know that that's right? So we had to verify, and that's what I'm going to reduce again for you right now. But first I'll look in the chat, I'm afraid, but I will. Yes, I was saying to the video. Oh my God. Okay, well, please do, private chat person. Like, again, I mean, I'm not above being a total. I want 100. Okay, please do, private chat person, and thank you, public chat person. Okay, that was yo. All right, I'm just going to read. I'm not going to say the person's name, but someone did say in private chat that just saying if I put that clip of me yodeling on TikTok, I'd get 100K so fast. I didn't know that was yodeling, but go, please have at it. I have no scruples when it comes to that, as everybody knows. Okay, so this is what we did last time, and and I think for some of you it took a little thought. Like, what I did was, remember, we said, and please bear with me, like, oh my God, I even know that. I can't believe I know that reference about yodeling in Walmart. And that is only because I have two crazy sons. I remember when the older son showed, that was years ago, wasn't it? I can't believe I know that. I'm so ashamed of myself, but yeah, I know what you're talking about. Oh God. And now the younger son, like, always wants to shop in Walmart because of Ryan, who I am a big fan of Ryan, actually. I have to admit, I know people think his whole family is totally corrupt, but I feel like if that's corruption in our society, we can do a lot worse. But anyway, okay. That's funny. I maybe I will. I'm not. Oh, maybe I will. Oh, you are my PR. Okay, I gotta stop reading the chat. But yes, okay. Yeah, last time they did this, they referred to me as the ADHD professor on TikTok, and you know, I didn't deny it half as much as I just presented it. But okay, luckily I was born before those. Anyway, okay, we had x equals x naught cosine omega t. That, remember, the differential equations is solving differential equations is like the game Jeopardy or the game show Jeopardy, in that really, in a way, the differential equation is like the answer, and we're trying to retrofit or like reverse engineer the question, like for real. Like the differential equation says, find a function that has this quality. Find a function that when you differentiate it twice, you get back like itself or some version of itself, right? It's not saying, here's a function, now differentiate it. It's saying, find a function such that when you differentiate it, blah, 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 blah. So we guessed a function, we guessed x equal, or we conjectured a function x equals x naught cosine omega t. But then the only way to find out whether that's right or not, the only way to make this valid is to differentiate it and see what happens, right? That's what we spent now. And that was uncomfortable for some of you, or new, or a walk down like weird memory lane for some of you. Like we had to take a couple of derivatives, and they're not totally trivial derivatives. Like hopefully they're sort of clear now. And again, any of you who still wants more differentiating sort of practice or reminders or help, please do contact me in private. And I'm not kidding about that. Like whether it's by text or private chat, like I will slow more down and walk you through the differentiate. But for many of you, I think it was just like you just needed your memory jogged and reminded, and now you see it again, I think. So we had to differentiate this function once, but then we had to differentiate it again, specifically twice, because the differential equation is second order. It says d2x dt squared equals blah, 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 blah. So what do we do? So we took the first derivative of this, and we said the first derivative, it looks like this because it's a trigonometric derivative and involves chain rule, right? Like that, I use like my memory of trigonometric, and that's something, again, on the side, I can show you. If you really think about it, it sort of makes sense. If you remember that a derivative is a slope, an instantaneous slope, it actually sort of makes sense that the derivative of sine is cosine and the derivative of cosine is sine, because when you're, but we can discuss this on the side in detail if you want, but just think of yourself walking along a sine function, like wherever the value of the sine function is really high, like at the top when the sine is 1, well, then the slopes are really low. Like at the top values of sine, you're at a local maximum, like you're neither going up anymore, nor are you going down. The tangent line would be horizontal, right? So when the value of sine is high, the derivative is super low, it's 0. Then as you're falling down the sine function, you're getting steeper and steeper. So the values get lower, but the derivative goes up, right? It sort of makes sense that the derivatives are alternating in that same pattern as the values themselves. This, in fact, kind of brings us back sort of to question 7, or I think it was 7 or 8 of the homework sheet. But anyway, the derivative of cosine is negative sine, and then chain rule brings out the omega. So then we did the derivative again. We did the derivative, and so chain rule applies again, but now we get cosine. Now we have to be a little careful. Please remember, and again, talk to me in private if you want a refresher on this, but I don't know if this is a memorizer thing or a conceptual understanding thing, but the derivative of sine is cosine. The derivative of cosine is negative sine, right? So I had a lot of questions about this last semester. Just let's be clear. First, I took the derivative of cosine. So a negative sign popped into my answer, like dx dt. A negative sign appeared. But now I have the derivative of, like, well, technically of negative sine, or if you just want to say I have the derivative of sine, and then there's a constant in front of it. When we take the derivative of sine, that does not produce a new negative sign. Like, right, I want to be very clear about this. Like the second derivative, in other words, did produce another omega, because we are doing chain rule again. So where, if you understand why that first omega came out in the first place, another one has now come out, so we get omega squared. But if you understood where that negative sign originally came from in the first derivative, we don't get another one now in the second derivative, because the derivative of sine is not negative cosine, it's just cosine. So the negative sign stays. That's actually super important. So we now have this, the second derivative of x with respect to t is negative x naught omega squared cosine omega t. Technically, I'm still reviewing here. Okay. So technically, I'm still reviewing. We have d2x dt squared equals that. Then I just do a little multiplication. I just do a little cleanup because I'm interested, because I'm interested in seeing. This is almost just about where we left off last Wednesday. I just, deploy the fact that multiplication is commutative. So I just multiply. So I just switch around the order of the omega squared and the x naught, right? So that's all I did. I just switched around the order. But why did I do that? Because I wanted to put together the x naught, the cosine of the omega t. I want to point out to myself, like, this whole business right here. And honestly, this step that I'm doing now is the step that tends to escape people on exams. Like, this is the one part that you got to see, or you have to remember to see that whole business right there is what we're conjecturing to be x, right? The whole thing is we're testing out whether x naught times cosine omega t does in fact work as an x according to this little verification procedure we're doing. The whole assumption of it is that x equals x naught cosine omega t. Therefore, according to this reasoning, evidently, here, I'll leave. Right now, let me slow down. We're almost there where we were Wednesday, but this is like a very big deal in my mind. What we're saying, apparently, by just taking two derivatives, by just like following calculus procedures, we're saying if we choose x naught cosine omega t to be x, then apparently that was a pretty interesting choice, because if we took one derivative of it, we just get this thing sine blah, we just get this function, and there's not much more to say about it. But if we took two derivatives of it, like the cosine went, then we get back a cosine, right? If we take two derivatives of it, we get back negative cosine. In fact, we get back the original function x times this thing omega squared. And I know we still don't quite know what omega squared is, but I'll tell you this, whatever it is, it's a constant, right? Omega squared was supposed to, omega was supposed to be some number measured in radians per second, some number that just multiplied by the t. It was supposed to be a constant. That's why it came out in the chain rule and all of that. Like, it's not a variable, it's a constant. I'm not saying I know exactly what it is yet, but I am just saying that omega is a constant, right? So omega was some freaking number measured in radians per second. Therefore, omega squared, it might look intimidating, like, oh my God, there's like squareds involved. What's happening? Is this like a quadratic now? Is this a parabola? No. It's not a parabola. It's not a quadratic. It's not as intimidating as it looks. It's just a number squared. And what do you get when you square a number? You get another number. In other words, what I'm saying, and this is important, I think, I'm saying this omega squared, whatever it is, and I'm trying to say it's super important, but don't let it intimidate you. I know it's a Greek letter, and I know we don't know what its value is yet. The reason we don't know what its value is yet is because it's going to be different for every different spring or every different oscillator. But for any given oscillator, it's going to remain the same for that oscillator. So omega squared is just the square of some constant. Omega squared itself is therefore just some constant. So look what happened. We did pick a good function, is what I'm saying. We picked a function such that when we took its second time derivative, we got back itself times some constant times a negative sign. That's what we wanted. I'm saying. Oops. I'm saying we were looking for some function such that when we took its derivative of its derivative with respect to time, we got back itself times some constant times a negative sign. The constant that we were talking about when we originally framed Hooke's law, the constant was, I keep saying some constant. What I really mean is some constant called K divided by some other constant called M. A constant, one number divided by another number is a number. Just like one number squared is a number. We wanted the second time derivative of X to be spit back X times a constant times a negative sign. What we got here when we guessed cosine was just that. We got that the function itself, when we took two time derivatives, we got back itself times some constant times a negative sign, i.e. our solution works, our cosine function works as long as what we're saying, well, yeah, I want to go to the next page, but we're saying, oh, great, our conjecture did work. Cosine is the right kind of function. As long as that omega that we stuck in, that we just knew it had to have certain units and we didn't know what number was, as long as that omega was just another name for what turns out to be another set of constants that we already know, k, the square root of k over m. As long as omega squared is one name for a constant and k over m is a different name for that same constant, then our solution works, which very bizarrely in a way means we just learned two things for the price of one. We just learned that our solution worked, and we learned in a way what numbers to plug in for that omega that started off being unknown. We solved our differential equation both in form, in general shape, and in details, in arbitrary constant. In other words, what I'm saying is, in order to just, if nothing else, just get a concrete answer to question 9, then what I'm really saying is if we wanted finally to get the plug and chug that we needed for question 9, this is the plug and chug we needed for question 9. Question 9 said, if t is 1, what's x? I'm saying, well, this is what we can plug into. X equals x naught times the cosine of omega. And what is omega? It turns out to be the square root of k over m times t. K, so k is 200 newtons per meter. 0.3 is the mass. 0.3 kilograms is the mass. 0.15 is x naught measured in meters. And if you do this on your calculator, I'll test it right now. But if you do this on your calculator in radian mode, so it's asking, I'm asking you if you want to get a final answer to question 9, and then we'll generalize this more. If you want to get a final answer to question 9, you want to do the cosine of whatever the square root of 200 over 0.3 is, but you want to make sure your calculator is in radian mode. You're taking the cosine of that number of radians and then multiplying it by 0.5. So in other words, I think it's, and I think the answer is 0.116, but I'll just make, I always say that and I never check. So yeah, omega here, I guess, right here. Oh, 0.118, okay. Okay, so first of all, what I'm, okay. So first of all, just to be concrete or to bring some closure to our lives, like the final answer to the final question of the first homework is, I believe, approximately 0.118 meters. I was saying approximately because there's square roots involved here and I'm chopping off digits. I'm not saying approximately because I'm like guessing, but we're chopping off digits from the square root. So it's approximately 0.118 meters. In other words, approximately less than 12 centimeters. Please do note that that's actually quite a reasonable answer. If I had gotten anything, and technically, oh no, that's quite a reasonable answer. And if I had gotten anything less than 0, do I want to say that? Well, I don't know about that. But if I had gotten anything greater, whose absolute value was greater than 0.15, something would be wrong and weird, right? This thing is only going to oscillate between 0.15 on one side through 0 all the way to negative 0.15 meters on the other side. So all right, I like the look of this answer, right? It's something between 0, whose magnitude is between 0 and 0.15. That's already nice. I also think it's correct because I plugged in to the cosine equation that I got. Now, what's the big takeaway here, though? The big takeaway is not the number 0.118. And the big takeaway isn't even, I mean, part of the takeaway is that omega equals the square root of k over m. Okay, I'll even write that. One thing that was kind of a breakthrough here, well, there was two things that were a breakthrough. One, we realized, okay, if we have this differential equation to solve, if we have a Hooke's law system, the solution is a cosine solution. That's definitely a big revelation already, that the position is going to oscillate cosinusoidally in time. By the way, you could say sinusoidally. You could say it's going to be a sine function too. But I keep saying cosine function because I don't think this thing starts at 0, 0. So I think cosine is ultimately more convenient and more preferable to sine. But that's like a tech, the big point is that this is a sinusoidal function. Okay, that's number one. The second point is that the details of the cosinusoidal function center heavily around this omega term. And in this case of the mass on the spring, the M on the K spring, it turned out that omega was nicely straightforwardly square root of K over M. You can memorize that if you want for a mass spring oscillator, but that's all that it is. Omega equals square root of K over M if you have a K, literally like a coil of metal, and you have an M at the end of it. What are we really saying in general? In general, we're saying this. Sorry, let me just make this smaller. I'm not changing, I'm just making it smaller. Sorry. Okay. The time. Okay, this is actually super important. I'm saying let's now blow up our conclusion. Like we're done with homework 1 finally, like as a homework assignment. We got a numerical answer to question 9, but what was really the point? The point is we had this, we knew some facts about x. We knew that the second derivative of x with respect to time had to equal x itself times some constant times a negative sign. So we played around and we conjectured and we verified that then that would work. That could all work. Hooke's law could be obeyed as long as x was some sort of cosine function of time. And by the way, again, think about it. Like that's actually not a surprise. Like the whole point is that that if you think about cosines, the derivative of a cosine is negative sine. The derivative of a negative sign is negative cosine. So cosine is precisely exactly that function, which when you differentiate it twice, you get back itself times a negative. Like that's totally what we're looking for here. I'm not saying it's the only one, by the way. I mean, truthfully, sine works as well. In fact, e to the x also works. I'm not saying it's the only one, but I'm saying it totally does work and it totally applies to our situation here. Well, I'm saying now in general, I don't care anymore about coils of metal on blocks of mass. I don't care even about specifically the Hooke's law that says F equals negative kx. I don't care about x. Let's say I've got any measurable, any conceivable, measurable, dependent variable. Could be angular position, could be electric field magnitude, could be temperature, anything that I could measure in the lab. If the second time derivative of that variable, if the rate of change of that variable equals some constant times that variable, but times a negative, then first of all, I'm viewing that as harmonic oscillation. Like if any variable at all, let me just make that clear here. So like if you were measuring the temperature of something in the lab and you found for however method, by whatever method, you found that the temperature, that the rate of change of the temperature, in other words, sort of like the acceleration of the temperature, right? If you found that that was always directly proportional to the temperature itself, and directly proportional means multiply is equal to the temperature itself times some constant. And then you found with a little more detail that whole proportionality was always multiplied by -1. If you found that there literally was a negative sign there, what I'm telling you right now is, well, that means that the temperature is oscillating harmonically. Like I'm saying, if you made a graph of that temperature, it would look exactly like the graph that we're making of the position of a mass on a spring or in time, or the position of a pendulum in time. Any system whose dependent variable varies in this way, any system whose second time derivative of the dependent variable is directly proportional to the dependent variable itself, but with a negative sign, is a harmonic oscillator. And therefore, for any harmonic oscillator, like in other words, it doesn't have to be physical. I mean, it's all physical, but it doesn't have to be visible. It could just be that this value, this thing that you're measuring is fluctuating up and down and up and down. If it's up and down this way, then the solution to its differential equation, then it, as a function of time, whatever it is, and I'm calling it z here, right? So I've switched, sorry, I should have. So I've switched from x to z on purpose, not just so I can switch from this axis to like this axis. I'm using, maybe I should use the letter Q or something here. I'm using z here to mean any frickin' measurable variable that you can imagine that varies in time. Like, please note, time is still my independent variable here. I'm not just a mathematician, though I play one on TV, on YouTube. I'm a physicist, right? So time is still my independent variable here. But I'm saying now, any measurable you want, if the measurable with respect to time can be described by this diffeq, this differential equation, then the measurable is oscillating cosinusoidally in time. And now, and I know we have 13 minutes, and here's the really subtle, I know I'm yelling, that must mean something. The subtle point is that the cosine expression will always have this omega in it. And for the next 13 minutes, I want to try to unpack this omega even further. Omega is not always the square root of k over m. It was when we had a k and when we had an m. We don't always have a k and an m. What omega always is, what I'm trying to say right here, omega is always the square root of whatever the constant in the differential equation is. So what I'm saying is, like I'm saying from now on, any differential equation we write that describes a harmonic oscillator, if it's a differential equation, it's got that constant of proportionality right before the variable. We're going to, from now on, write that constant as omega squared. We're writing it as the square of some number. Obviously, maybe not obviously, but certainly the square of some number is still just a number. Like I don't have to call it omega squared. In the case of the mass on the spring, I called it K over M. In the case of a pendulum, I might end up calling it G over L, or you might already know that. Or in the case of something else, I might call it something else. But whatever it is, I can and I will, in fact, abbreviate it omega squared, because what I'm saying in advance is whatever that constant is, whatever that constant of proportionality is, the square root of it is going to be the radians per second rate winds up in the cosine function. But why? Because when we differentiate twice, the chain rule will bring out that omega twice. So for this all to work, the seemingly unknown constant that we just know has to be there to convert seconds into radians, that unknown constant, what that is necessarily is the square root of whatever the proportionality constant was in the differential equation. So from now on, and again, I'm going to try to unpack this more for 11 minutes. I really want to see what this omega is all about. But what I'm saying is, one thing about this omega is it's always just the square root of whatever was the multiplier before the dependent variable in whatever oscillator we're talking about in the differential equation that describes any oscillator we're talking about. So, okay, so I'm going to go, so now I'm going to say, but okay, but what is really the omega? Okay, so I'm saying omega is important, okay? For any differential equation, I'm sorry, for any simple harmonic oscillator, you can describe it with the second order differential equation. D2 variable over dt squared equals negative times omega squared times the variable. What is omega squared? Well, for one thing, it's just a funny way of writing whatever K over M or L over G or whatever appears there. But for another thing, it's the square root of what I'm about to tell you. And this is the part that's definitely relevant to tomorrow's lab. Okay, what omega is? So again, remember, omega only even appeared. We only even knew to put in omega, and it's just a Greek letter. It could have been any letter. But what it stood for was some sort of constant number that we felt had to be multiplied by the t in the cosine expression so as to cancel out the seconds and leave us with radians. Sorry. Yes, very, very awesome direct chat person. Please submit this for participation. Yes, yes, yes. Also, I'm not going to read the person's name, but I'm going to read the thing that someone in the direct chat just said. So is omega kind of like the period? Now that is a perfect, sorry, let me say that more clearly. They said, so is omega kind of like the period? Period as in period of time. Period as in amount of time for one cycle. Let me say what's perfect about that question is that the answer is perfectly yes. Omega is kind of like the period. It's super related. In fact, if you even look back at the first page of notes, or what my ultimate like punchline for this whole lecture today, like within 7 minutes, what I want to show you is exactly how omega is exactly related to the period. And then again, let me applaud this direct chat question here. Like, I'm not saying omega is the period, and neither is the person asking the question. I mean, he or she is not saying that. But I am saying, oh, if you can kind of picture what period means, if you picture that period is the amount of time it takes us to do a cycle, let me back up even further. We're talking about an oscillator here. In all these cases, whether it's a mass on a spring or a pendulum, we're talking about something that's oscillating back and forth. That's something that is doing something cyclical, periodic, repeated, right? So ultimately, the most handy way to talk about these oscillating systems is to talk about the rate at which they are cycling. All other kind of rates, and please do remember this, the reason I'm making a big deal about differential equations and omegas and cycling rates is because what we found in all the first 8 questions of homework 1 is our standard ways of talking about motion are all like applicable and relevant in super interesting ways, but they're not directly convenient or helpful for an oscillator. All of our standard things like position, velocity, acceleration, even jerk, even whip, like even if we want to go to third derivatives, fourth derivatives, fifth, they're all sort of fascinatingly in chaos. They're not literally in chaos. They're all in, like, in other words, every single moment of an oscillator, the position's changing, the velocity's changing, the acceleration's changing, the jerk, everything is changing smoothly all the time. So we can't capture the whole oscillator with one thing like acceleration or jerk. They're all changing, but we can talk about the rate at which they're cycling. We can talk about things like how much time does it take to complete a full there and back cycle. That would be called the period. That is what someone's asking about in the direct chat. I'm going to totally reference that explicitly in like 2 minutes. But yes, absolutely, the most direct way to picture and measure anything that's cycling is to talk about the period of time that it takes to go there and back. Okay, in fact, yeah, let's go from there. I'm going to go from the direct chat person's question. Like yes, capital T. So again, I'm saying it's a great question. It actually helps me teach this better now, for real. The question that someone asked was, is omega kind of like period? And my very firm, excited answer is, oh yes, it is it's very related to the period. I don't want to say they're identical. They're super related. Let me show you the relationship. So the reason I'm excited about that question too is that person's not crazy for asking that. He's like she is like every other physicist who, for all of us, period is the easiest thing to relate to in an oscillator because it's the easiest thing to measure. That's why you spent like 2 labs or something sort of poking around and trying to measure it, because you could just get an oscillator going, you get it going, and then you start your stopwatch when the oscillator's already at an amplitude position, and you let it go like 20 swings and you measure the amount of time and you divide by 20, right? That, for all of us, that's the easiest identifier on some nice rhythmic oscillator. So T, capital T from here on in stands for period of time for one cycle, which means like round trip, right? There and back. Like a cycle means end up back where you started, right? So the units of period for sure are seconds, or technically you could say seconds per cycle. Now let's be careful now right away. Cycle is not an actual MKS unit, right? I'm just like writing it as it's not really a unit, but period would be measuring the number of seconds per some cycle. We can immediately define then, if you can picture, and that's the easiest thing to measure, it is, period. But then we can set up something called lowercase, this is a lowercase f. Okay, I don't know how you want to draw it. This is not the F meaning function, nor is it the F meaning friction. You can set up a lowercase f, which is and I know I have 3 minutes left. you can set up, or you could think about something called standard frequency. So we're almost at the punchline here. Standard frequency, lowercase f, which wouldn't be seconds per cycle. It would be the opposite of that, cycles per second, right? And in fact, just as you would expect, exactly as you would hope, necessarily, like by definition, F and T are reciprocals, are multiplicative inverses of each other. In other words, if it takes me 4 seconds to do a full cycle, then I'm doing 1/4 cycles per second. Okay, and I know I have 2 minutes. So period is measured in seconds per cycle. It's the easiest thing to measure in the lab. But one step away from that analytically is standard frequency, which would be measured in cycles per second. But please note also that we have this thing from here on, because it's such an important thing, frequency, we define this thing called a hertz, which is 1 cycle per second, okay? And so like 1 megahertz, like on the radio or whatever, equals by definition 1 million cycles per second. I have to do this a little bit fast because I know we're just about out of time. But so now we've got period, and then the reverse, the inverse of that is standard frequency. Well, then what's omega? Omega is going to be what we call angular frequency. Omega is the thing that's least physically intuitive, but most mathematically direct. Omega comes up, and I know I have 1 minute, let me just say this, and omega comes up when we want to understand all the mathematics of a cycle by using the convenient math we already have developed for circles. Omega and cosines and sines all come up because we already have a whole mathematical understanding of circles. If we just graphed our understanding of circles onto cycles, we don't have to reinvent the wheel, no pun intended. And what do I mean when I say graphed the mathematics of circles onto cycles? What I mean is that an angle is just a fraction of a circle, right? A 360 is a full circle. A 90-degree angle, when you really think about it, is a fourth of a circle, regardless of how big the circle is, regardless of the radius. Everybody actually recognizes if you think about it, don't think of an angle. And I know I've got 1 minute. Sorry, if you have to go, go. I'm just about done, but we're just about done. It'll help you a lot for tomorrow. You have to go, go. But if not, bear with me for like a minute and a half. Don't think of angles as intersections between lines. Like you can, but what's much more helpful is to realize what's universal about an angle is that it is a section of a circle. My 7-year-old son knows what a 360 is because he could see them like in video games and skateboards, right? Yes, have a great day if you have to go, if you have to go. I'm just about done, but yes, if you have to go, 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 go. Listen, an angle from here on in is a portion of a circle. If you can divide circles into 360 parts if you want, or take care, or you can. Okay, all right. Well, I'm just going to write this then. Here, what I'm saying is this. To wrap this up, I'm saying what's omega? It's 2 pi times f. Omega is the number of radians per second. There's 2 pi radians in every cycle. If your standard frequency, if you're doing 1 hertz, if you're doing 1 cycle per second, if that's your frequency, then you're doing 2 pi radians per second. Just from now on, understand there's 2 pi radians to every cycle. So angular frequency is just frequency multiplied by 2 pi. Pi is half a circle, pi over 2 is a quarter of a circle, 2 pi is a full circle or a full cycle. And we take cosines of these things, of portions of circles. So there are 2 pi radians to a circle. What is a radian? It's a sixth of a circle, because 2 times pi is essentially 6. A radian is a little bit less than 60 degrees. It's a little bit less than a sixth of a circle, a sixth of a cycle, I should say. A radian is a sixth of a cycle. That's all it is. So when we say your angular frequency is 7 radians per second, we're just saying you're doing a little bit more than 1 cycle per second. That's it. So okay. Sorry to keep you guys. Thank you for staying. Those of you who did. I'll see you in 2 days. Have a good lab. Thank you. Sorry to keep you. Thank you. I'm done. Okay. something. Anyway, he's still. Yeah, and so to that direct chapter, so omega is 2 pi over the period. Over the period. Okay, thank you guys very much. Thank you guys for hanging out. You too. I appreciate it. Sorry that was rushed in, but boy, people can't even give me a minute and a half here. Okay. Okay. And you should, okay, I'm stopping recording.